Welcome to Section 7, Lesson 5. In the previous 4 lessons, we covered polynomial vocabulary, addition, subtraction, multiplication, and the special product identities. Today, we tackle polynomial division using the long division algorithm. The mechanic is identical to the long division algorithm you learned in elementary school for integers: divide leading term by leading term, multiply, subtract, bring down, and repeat until the remainder degree is smaller than the divisor degree. The fundamental relationship that emerges is dividend equals quotient times divisor plus remainder, which is the polynomial version of the division algorithm for integers. Today, we lock in the long division mechanic, the stopping rule, and the standard form presentation of the quotient and remainder. First idea on the board. The long division algorithm for polynomials follows 5 steps repeated until the remainder is small enough. Step 1. Divide the leading term of the current dividend by the leading term of the divisor. The result is the next term of the quotient. Step 2. Multiply the entire divisor by that quotient term and write the product directly underneath the current dividend, aligned by exponent. Step 3. Subtract the product from the current dividend, distributing the negative through every term. Step 4. Bring down the next term of the original dividend, if any. Step 5. Repeat with the new current dividend until its degree drops below the degree of the divisor. The final remainder has lower degree than the divisor by construction. Second idea, the fundamental division relationship. After polynomial long division, we have dividend equals quotient times divisor plus remainder. This is exactly the integer division algorithm extended to polynomials, where the remainder satisfies a degree constraint instead of a magnitude constraint. The relationship lets us check polynomial division by multiplying back, take the quotient times the divisor, add the remainder, and the result must equal the original dividend exactly. Multiplication and add verification is the foundation of polynomial division correctness checking and is recommended on every problem until the mechanic is fluent. Third idea, setup conventions. Before starting long division, write both the dividend and the divisor in standard form, descending order by exponent. Insert 0 placeholders for any missing exponents in the dividend. For example, x cubed plus 1 as a dividend should be written as x cubed plus 0x squared plus 0x plus 1, so that subtraction lines up term by term. Without 0 placeholders, the alignment of the long division work breaks down and arithmetic mistakes become almost guaranteed. Today, we drill the long division mechanic on 2 worked examples, including one that requires 0 placeholders, and lock in the algorithm for the rest of Section 7. Polynomial long division uses the same 5-step algorithm as integer long division. Divide leading term by leading term to get the next quotient term. Multiply the divisor by that quotient term. Subtract from the current dividend. Bring down the next term. Repeat until the remainder degree is smaller than the divisor degree. The 5 steps in detail. Step 1. Divide the leading term of the dividend by the leading term of the divisor. This becomes the next term of the quotient. Step 2. Multiply the entire divisor by that new quotient term and write the product underneath the current dividend lined up by exponent column. Step 3. Subtract the product from the dividend, distributing the negative sign through every term of the product before combining. Step 4. Bring down the next remaining term of the original dividend. Step 5. Check whether the new current dividend has degree less than the divisor. If so, stop. If not, return to Step 1 with the current dividend. The fundamental relationship at the end is dividend equals quotient times divisor plus remainder, where the remainder has degree strictly less than the divisor. This is exactly the integer division algorithm extended to polynomials with degree as the size measure. The relationship is symmetric and lets you verify any polynomial division by multiplication and add compute quotient times divisor, add remainder, and check the result equals the dividend. Setup convention. Before starting, write both dividend and divisor in standard form, descending order by exponent. Insert 0 placeholders for any missing exponents in the dividend. The placeholders are essential for column alignment during subtraction. Without them, the positional arithmetic breaks down and term mismatch errors become almost certain. The placeholders cost nothing because 0 times any divisor term is 0, but they make the algorithm work cleanly. Stopping rule: the algorithm terminates when the remainder degree is strictly less than the divisor degree. At that point, the remainder cannot be divided by the divisor any further within polynomial arithmetic. The quotient is fully constructed by then, and the remainder sits at the bottom of the work. Today we drill the algorithm on 2 worked examples and lock in the mechanic for the rest of section 7. Here is the first worked example. Divide the polynomial 2x cubed plus 3x squared minus 8x plus 4 by the polynomial x minus 2 using long division. Both polynomials are in standard form already, no 0 placeholders needed. Step 1. Divide leading by leading. 2x cubed divided by x equals 2x squared. This is the first term of the quotient. Multiply the divisor x minus 2 by 2x squared, x cubed minus 4x squared. Subtract this from the dividend 2x cubed plus 3x squared minus the quantity 2x squared minus 4x squared equals 0 plus 7x squared. Bring down the next term minus 8x. Current dividend becomes 7x squared minus 8x. Step 2. Divide leading by leading again. 7x squared divided by x equals 7x. This is the second term of the quotient. Multiply the divisor x minus 2 by 7x, see 7x squared minus 14x. Subtract 7x squared minus 8x minus the quantity 7x squared minus 14x equals 0 plus 6x. Bring down the next term plus 4. Current dividend becomes 6x plus 4. Step 3. Divide leading by leading once more. 6x divided by x equals 6. This is the third term of the quotient. Multiply the divisor x minus 2 by 6x minus 12. Subtract 6x plus 4 minus the quantity 6x minus 12 equals 0 plus 16. Current remainder is 16, which has degree 0 less than divisor degree 1. Stop. Step 4. Read off the result. The quotient is 2x squared plus 7x plus 6. The remainder is 16. Write the answer in the form dividend equals quotient times divisor plus remainder 2x cubed plus 3x squared minus 8x plus 4 equals the quantity 2x squared plus 7x plus 6 times the quantity x minus 2 plus 16. Step 5. Verify by multiplication. Multiply 2x squared plus 7 by x plus 6 by x minus cube plus 7x squared plus 6, x minus 4x squared minus 14x minus 12, which collapses to 2x cubed plus 3x squared minus 8x minus 12. Add the remainder 16, 2x cubed plus 3x squared minus 12 plus 16 equals 2x cubed plus 3x squared minus 8x plus 4. This matches the original dividend exactly. The division checks out. So the quotient is 2x squared plus 7x plus 6 and the remainder is 16. The big lesson from this example is that polynomial long division is a mechanical algorithm: divide, multiply, subtract, bring down, repeat. The 5-step cycle terminates when the remainder degree drops below the divisor degree. Multiplication and add verification at the end provides a reliable correctness check on every division problem. Here is a second worked example, this time with a missing term 0 placeholder. Divide the polynomial x to the 4th minus 3x squared plus 4 by the polynomial x squared plus 1. The dividend has missing x cubed and x terms. We will insert 0 placeholders for them before starting. Step 1. Setup. Rewrite the dividend with 0 placeholders: x to the 4th plus 0x cubed minus 3x squared plus 0x plus 4. Now every exponent from 4 down to 0 is represented, ensuring proper column alignment during the long division work. Step 2. First iteration. Divide leading x to the 4th divided by x squared equals x squared. This is the first term of the quotient. Multiply divisor by x squared times the quantity x squared plus 1 equals x to the fourth plus x squared. Subtract from dividend x to the fourth plus 0x cubed minus 3x squared minus the quantity x to the fourth plus 0x cubed plus x squared equals 0 plus 0x cubed minus 4x squared. Bring down 0x, the current dividend becomes negative 4x squared plus 0x. Step 3. Second iteration. Divide leading negative 4x squared divided by x squared equals negative 4. This is the second term of the quotient. Multiply divisor by negative 4 times the quantity x squared plus 1 equals negative 4x squared minus 4. Subtract negative 4x squared plus 0x minus the quantity negative 4x squared plus 0x minus 4 equals 0 plus 0x plus 4. Bring down nothing more. Wait, we still have plus 4 left from the original dividend. Let me redo. After the first iteration we had brought down 0x. The current dividend was negative 4x squared plus 0x. In the second iteration we bring down the constant 4. The current dividend becomes negative 4x squared plus 0x plus 4. Subtract divisor times negative 4 equals negative 4x squared minus 4. Result negative 4x squared plus 0x plus 4 minus the quantity negative 4x squared minus 4 equals 0 plus 0x plus 8. Current remainder is 8. Step 4. Stopping rule. The remainder is 8 degree 0 less than divisor degree 2. Stop. The quotient is x squared minus 4. The remainder is 8. Step 5. Verify by multiplication. Multiply x squared minus 4 times x squared plus 1x to the fourth plus x squared minus 4x squared minus 4 equals x to the fourth minus 3x squared minus 4. Add the remainder 8x to the fourth minus 3x squared minus 4 plus 8 equals x to the fourth minus 3x squared plus 4. This matches the original dividend exactly. The division checks out. So the quotient is x squared minus 4 and the remainder is 8. The big lesson from this example is that zero placeholders for missing exponents are essential whenever the dividend has any gaps in the exponent sequence. Skipping placeholders breaks column alignment and almost always corrupts the result. Inserting them costs nothing and makes the algorithm robust. 3 mistakes that catch every algebra student during their first weeks of polynomial long division work. Each one is fixable with a small explicit habit applied on every problem from now on consistently. First mistake. Skipping zero placeholders for missing exponents in the dividend. A student writes x cubed plus 1 as the dividend and starts long dividing without inserting 0x squared plus 0x in the middle. The columns of the work go out of alignment, the subtractions cross terms of the wrong exponent, and the answer is corrupted. The fix is to always rewrite the dividend with explicit zero placeholders for every missing exponent before starting any division work. Zero placeholders cost nothing and prevent the entire alignment error category. Second mistake, forgetting to distribute the negative sign through every term of the multiplied product during the subtract step. A student computes the product and writes it underneath, then subtracts only the first term, leaving the rest as additions. The mistake exactly mirrors the polynomial subtraction mistake from lesson 2, not distributing the negative through every term. The fix is to always rewrite the subtraction explicitly as adding the negation of the product, then perform the addition term by term with the negation already absorbed into each coefficient. Third mistake. Stopping the algorithm at the wrong time, either too early or too late. A student stops when the current dividend has the same degree as the divisor, when actually the rule is to stop when the remainder has strictly less degree. Or a student continues past the stopping point, dividing into a remainder of lower degree and getting fractional or otherwise nonsensical quotient terms. The fix is to internalize the stopping rule, precisely stop when remainder degree is strictly less than divisor degree, equivalently when the remainder cannot be divided by the divisor any further within polynomial arithmetic. Polynomial long division shows up across calculus, partial fractions, root finding, and computer algebra continuously. 4 broad sectors below where every working professional applies this division operation routinely. In partial fractions, decomposition in calculus and ordinary differential equations, an improper rational function with numerator degree greater than or equal to denominator degree must be reduced first by polynomial long division. The division produces a polynomial part and a proper rational part, and only the proper rational part undergoes the partial fractions decomposition step. Without the long division reduction, the partial fractions algorithm cannot proceed. In polynomial root finding, once a single root r of a polynomial p of x has been found, the polynomial divides evenly by the linear factor x minus r by the factor theorem. The quotient polynomial p of x divided by x minus r has degree 1 less than the original, and its roots are the remaining roots of p, repeated root finding, and dividing reduces the original problem step by step until all roots are found. Polynomial long division is the workhorse of this reduction. In calculus integration, rational functions are integrated by first reducing improper to proper via polynomial long division, then decomposing the proper part by partial fractions, then integrating each piece. The long division step is the gateway to the entire rational function integration technique, which appears continuously in differential equations, applied math, and engineering calculations. In computer algebra systems and polynomial computer algebra libraries, the Euclidean algorithm for polynomial greatest common divisors is built on top of repeated polynomial long division. Symbolic computation libraries use the same algorithm to simplify rational expressions, factor polynomials, and solve algebraic systems. The long division mechanic from this lesson is the foundation of essentially all polynomial computer algebra. 3 things to take with you from this lesson today. Polynomial long division is the polynomial extension of the integer long division algorithm and is one of the most useful operations in algebra and calculus. Today's mechanic is the foundation of synthetic division, the remainder and factor theorems, and the rational root theorem in the next lessons. First, the algorithm has 5 repeated steps. Divide by leading to get the next quotient term, multiply the entire divisor by that quotient term, subtract the product from the current dividend, distributing the negative through every term, bring down the next term of the original dividend, repeat with the new current dividend. The algorithm terminates when the remainder has degree strictly less than the divisor. The quotient is fully constructed by termination, and the final remainder sits at the bottom of the work. Second, the fundamental relationship at the end is dividend equals quotient times divisor plus remainder, exactly mirroring the integer division algorithm. The relationship lets you verify any polynomial division by multiplication and add compute quotient times divisor, add remainder, and check the result equals the original dividend exactly. Verification is recommended on every problem until the mechanic flows fluently. Third, always write both dividend and divisor in standard form before starting and insert 0 placeholders for every missing exponent in the dividend. 0 placeholders are essential for column alignment during the subtraction steps. Without them, the positional arithmetic almost always corrupts the answer through term mismatch errors. Coming up next, the lesson called synthetic division, which is a fast shorthand for long division when the divisor is linear of the form x minus c. Synthetic division uses just the coefficients without the variable letters, organized in a compact tableau that makes the division mechanical and very fast. The lesson teaches this shorthand alongside the connection to the remainder theorem of the next lesson.